Welcome to DV Club on the 25th of April. Today we're going to be discussing performance testing and analysis. We have 112 attendees today, representing 76 different companies across 21 countries. And we have two speakers today. I'm going to be very quick so we can make Nick Heaton get on with his talk from Cadence Design Systems, and then he'll have half an hour, and then we'll switch over to David Kelf from SoC Verification Systems, and we will be finished by 1 o'clock. A quick thank you to our speakers, our sponsors, as well as our two speakers, of course, Agnesis, Cadence Synopsys, Bracknell, Impress, ARM and ST are our venue sponsors, and hopefully we'll be able to go back to live venues at some point, but at the moment we're still fully online. And thank you to Tessolve, who are my employer. Okay, so we'll switch to our first speaker, if we can, please. Tisha?
I will make the presenter to Nick now. Nick, there will be a pop-up message on your screen.
Thanks, Nick. Do you want to go full screen, Nick, please? Hi, Nick. Do you want to go full screen? Perfect. Thank you. Right. So our first speaker today is Nick Heaton from Cadence Design Systems, where he is a distinguished engineer. He's going to be speaking about SoC verification in a multi-chip, multi-die world. Nick is an ASIC and EDA veteran, that's his words, not mine, veteran with more than 30 years. He graduated from Brunel University in London in 1983 with a first-class honours degree in engineering and management systems. He currently works in the systems and verification group at Cadence and is responsible for SoC verification and the architect of system verification IP. He's located in Cambridge today. Over to you. Thank you, Nick.
Actually, I'm not in Cambridge, Mike. There's a change of plan, but I'm in Cork, my home, my current home. Okay. So what I wanted to do is talk. Obviously, we've got a fairly brief session here. I'm not going to talk particularly about the motivation for multi-die, but hopefully that's a topic that's fairly clear to people, that you know, in terms of yields and packaging, that chiplets and multi-die technology is really becoming more mainstream, and hence the reason for one of the reasons for this discussion. I've been working on system performance for about 10 years, mostly on ARM systems, but I wanted to share some of the challenges that are faced when you start to look at systems. Obviously, the bleeding edge guys are really driving a lot of the work that's being done, but as with any of these things in our industry, they tend to waterfall down to the more regular designs, and so this is sort of an inevitability that a lot of things and challenges that are being faced at the high end are going to become mainstream challenges, and we've seen that cycle over a number of years. So I'm going to briefly talk about single die performance, and then introduce die-to-die connections. So specifically, I'll just introduce some aspects of UCIe, but there are multiple flavors of die-to-die connection. Look at the different kinds of die-to-die systems, and you know, the similarities and differences, and what we actually need from a solution, what the industry needs from EDA, as it were, to help solve some of these problems. So that's kind of the overview of what I'm going to talk about. In a very stylized simplified diagram of a system, and this is really a CPU subsystem. It's not obviously an overall full system. You can focus in terms of performance really on the main core of the system, which is the various clusters, caches, interconnects, whether they're non-coherent or coherent, and DDR controllers. This is the mainstream. Obviously, different domains vary in terms of their performance challenges, but these are some of the most common industry challenges. Are ensuring that your system delivers. I'm old enough, as Mike said. I've been working in this space for an awful long time, working with ARM since the late 90s. And in the good old days, you just had to figure out which ARM core you needed in terms of power and performance requirements, and usually it was driven in the early days by area. So how much silicon space did you have will determine what core you were going to use, and your performance was pretty much set in stone by the decisions you made as to which core, and that was the dominant factor. About 10 years ago, things started to change dramatically as we saw the end of Moore's law and the fact that we went to a multi-core system. Initially was again managed by ARM, and the cores were contained within a cluster that was all nicely packaged, and the caches were managed for us. But once that broke down, and the customer was then in charge of deciding how many cores, which were coherent, what the coherency domains were, all of these problems started to become significant. And it's interesting that this is the DV club, but we're talking about performance, because I think a lot of people might think that the architects do their architecting and do performance exploration and determine what the performance is going to be and write the specs, and then we're all good. Well, the reality is that a lot of the performance testing, for a very specific reason, tends to fall on the verification engineers, because they're the guys who are doing cycle accurate measurements. A lot of the architecture exploration is done in System C, TLM, with approximate models, where some of the performance details, for good reason, are left out so that they run fast and you can do a lot of software modeling. Unfortunately, they have a significant impact on the performance of the system. So the one place where you're going to get accurate performance measurements is in RTL. That's where the verification engineer is the king, and so the task suddenly falls on the shoulders of verification engineers. And that's what I've seen as an evolving trend over the last 5+ years, and it's still a trend. Not everybody has performance as a number one, but it tends to fall on the verification guys. And why is this becoming problematic, I guess, is, this is what we're talking about today. So we're getting more and more cores, and the newer cores are becoming more aggressive in their prefetch mechanisms. So in order to squeeze the kind of high-end performance that's required for systems, the prefetchers, the speculative prefetchers in the cores, becoming more and more aggressive. They're fetching code way ahead of where the core's executing, to the extent that you might have 100 outstanding fetches ahead of where you're actually executing. That's great for performance, but because of the nature of speculative execution, you're actually wasting bandwidth by doing that. So obviously, if your system isn't fully loaded, it's good memory bandwidth to use to improve your throughput. But as the system becomes loaded, it might be one of the things that you want to throttle back. And so there are mechanisms now being added to do that. All of this data, is going to go through, and again, in the good old days, you might have a single DDR controller. So your job was really optimizing access from one core or one or two cores through a DDR controller. And these controllers are highly optimized for throughput, but they make a lot of assumptions about the nature of the traffic. And so you want to be able to validate the interconnect and the DDR together, because they're probably from different suppliers, and that all of the configuration of those components is not causing you performance problems. As I said, there are now emerging, and some of these specs, the ARM MemPan spec and the Intel RDT spec, have been around for quite some time. The architecture specs tend to take a little while to filter into the wild, and we see IP coming out supporting it 3 or 4 years after the specs are released. These specifications really are to do software controlled or software management performance allocation. So this is very much a trend inside the infrastructure systems, where you've got huge control numbers of cores and you're trying to optimize throughput for a number of virtual machines. The software can actually allocate memory bandwidths or caching to a group of cores that are software configurable. This is great because it means it's a software configured system. There's an agreed standard and a hypervisor can support it. But now you, as a performance verification guy, you need to check that these mechanisms work. And those mechanisms impact the DDR controllers, the interconnect, and the cores that are connected to them. So this is really a system challenge that you need to go and explore and ensure that the bandwidth allocation and the cache allocations that the software has given a group of threads is actually being enforced. So what all of this means, it means it's increasingly hard to predict the real world peak performance and the sustainable system performance. Hard to know what the worst case latency might be, or the average latency. So for applications where, turnaround latency of access is key, and in real-time responsiveness, that could be an issue. And it's increasingly easy to accidentally throttle the performance. Obviously, this diagram is very simplified. There are clock domain bridges, there are power domain bridges, there are cascaded layers of interconnect in the systems. All of these things, along with all the configuration of this IP, for example, what hashing algorithm are you using to spread the workload across multiple DDR controllers? How do you ensure that you've configured it correctly and it doesn't affect the system performance you're expecting? And obviously, one of the first things you want to do is understand all the permutations of paths, and this is why this is becoming increasingly complicated. If you're in a non-coherent traffic scenario, so you're not using the caches, relatively simple. You look at the paths to memory and you can measure the bandwidth latency. If you're in a coherent system and you've got caches in the picture, then what's the range of cache hits and misses? And you might want to, do a spread of cache hit miss ratios and see at what point you get differing performance limits. And a lot of this requires analysis tools, and obviously creating these scenarios is an issue. But you may end up with a situation where you're running a test and you've got a load of initialization. This graph kind of shows you've got a lot of initialization traffic just configuring your system. And then maybe there's a period when you're warming the cache because you can't do realistic cache hit miss testing without preloading the cache in some way to define the cache hit miss, and then analyzing bandwidth, latency. I know it's an eye test, but we've got bandwidth, latency, and outstanding transactions, which is a measure of the number of transactions that a particular initiator has issued and is waiting to complete. All of the modern systems really for the last 10 years have supported protocols that have multiple transactions in flight, and that's why this analysis becomes quite complex, because all of the transactions are overlapping each other concurrently. And so you need something to really understand the statistical picture as much as the precise clock cycle latency. So at the low level, they look predictable to these systems in clock cycle terms, but in reality, they behave almost like analog systems, in that you've got huge numbers of transactions injected into the system, and they're all competing for some kind of restricted resources, whether it's memory bandwidth, whether it's cache occupancy, or whatever. So when this problem scales up to multi-die, we need a die-to-die connection. So I've just shown here, just to introduce something. I mean, UCIe is a really, really hot topic at the moment, but it's not the only way of connecting dies together. I want to stress that. But in a UCIe system, you've got a UCIe controller, which is really a transport mechanism that can sit under other protocols. So it could sit under PCI Express, it could sit under CXL, it can be used in a native streaming mechanism, and this gives you options as to what the communication mechanism is from die to die, and this allows you to create either homogeneous systems or heterogeneous systems. And so, for example, what do we mean by a homogeneous system? Well, this is where we've got something like a symmetric multiprocessor. So our compute subsystem now has gone from being contained on one die to being replicated and connected together, and the intention is it can look like one compute subsystem, even though it physically resides on multiple dies. And in this particular instance, we could use the streaming interface of UCIe to provide coherent traffic, where potentially a core can access a cache on its adjacent die, or connect through to the DDR eventually on an adjacent die, or connect locally. So the challenge now is not only that we've got all of the paths within the compute subsystem, we've got a whole set of paths that go in various hops across die to die. And again, we've introduced more potential throttle points into our system. And so it's really important to understand what's going on in your system, what kind, creating stress tests that reflect how you believe the system is going to behave. And then you need to understand if there are bandwidth throttling issues, you need to be able to investigate where they might be and somehow figure out information that could be a proxy, so I can find the point of throttling. And this is how we use outstanding transaction count, is a really useful proxy, because it will saturate at a certain interface if there's a blockage. And so visualizing that at all the points in the paths is really key to understanding how you will actually debug a bandwidth issue. The knock-on effect of these throttles is also you may see latency go up, because there's you're strangling the system, and so both statistical latency analysis but also over time-based analysis is required. And the localization of your data becomes really important. Obviously, if you're operating a thread in the right-hand side, then let me see if I can, right here we can get highlighted. So if you're operating a thread on a core here, ideally you want all your data in this cache and potentially in this memory system rather than it having to go across. Now, you know, that's a significant hardware mechanism to support ensuring that there is coherency between these caches. So firstly, setting up scenarios to stress this, and then understanding the consequences. These are complex problems. And so you need good tools to do both of those activities. Oops, sorry, how do I undo my highlighting? Okay. Okay, so if we switch from, so in the previous slide we had a homogeneous system. So the two dies left and right look very similar, right? They can be more or less identical. In a heterogeneous system, we're really saying, right, we've got a compute subsystem on the left, but maybe we've got some kind of accelerator. So this might look like a PCI Express endpoint, for example. And in this case, we're using the PCIe flavor of UCIe, and the right-hand side could be, you know, it could be a high-speed networking system, it could be a storage system, it could be whatever you connect, it could be a graphics system, whatever you connect to your PCI Express typically. And this is going beyond the, you know, the hyperscaler kind of applications. This is the kind of thing you might see in automotive, where you've got a compute system and then you need some kind of, maybe some machine learning accelerator that needs to sit on a separate die. And you can connect it as a PCIe peripheral, and, you know, however you want to set it up. Now, the problems, the challenges from a performance point of view are very, very similar. You've got lots of potential throttle points again. You've got the same problem of visualization or whatever, but you're now got in a situation where you've got packet assembly and decomposition across here. That's at a higher level of abstraction. So we're now transmitting PCIe data. You've also got the challenge that you have to bring up the PCIe interface IP, potentially, you know, enumerate the bus, and anyone who's done any PCI Express work will know this is a lot of baggage. So a system like this, although it looks very similar, really introduces a heavy cost in terms of configuring these two chips so that you can actually get them to operate together. And that's a lot of software, and it's potentially a lot of bare metal software if that's the level you're actually trying to measure performance at. Because you probably want to do a lot of this stuff before you've brought up your OS. So the left-hand side will probably have some kind of operating system you'd want to boot, but you might want to do a lot of this testing with either a full die model or a partial die model to actually, and the typical approach here is you use some kind of partial model, usually on the right, with a fairly full model on the left, so that you can assess the bring up software, and then, you know, you can alternate. Depends if you're designing both sides of this. In a homogeneous system, you're generally designing the same die is used in a replicated use case. In this case, you know, again, you might be designing both of the die, but I think the vision a lot of the semiconductor guys have is that a market for potentially commercial chiplets that you'll be able to buy and stitch together is how they see this thing evolving. And so the idea that the chiplet on the right might be something you buy off the shelf, and you're developing the chiplet on the left, or vice versa, means you've got worry about both verification of that model, but also how's it going to perform, and have you got a performance model of the piece that you're buying in? So obviously the paths, again, very similar, just initiated in this case by maybe a PCIe at one end, going to a cache, going to an, or it could be from an accelerator, going to across this interface. So the traffic on the die-to-die interface is going to be a potential mix of PCIe traffic. It could be cache coherent maintenance traffic going across it, whatever. And the way this is evolving in the market, the way I see it is that, and there's going to be multiple UCIe connections between dies. It's not like there's going to be one. This is a very simplified diagram. A lot of the customers I'm dealing with are talking about, 4+ UCIe interfaces on each chiplet to connect different things together or to extend the bandwidth. And again, if you're putting traffic spread across multiple interfaces, that's something you want to analyze and understand and create stress tests for. So in summary, we need something to create stress scenarios, and there are a lot of details here that become quite important when you're creating stress scenarios, and this is something Cadence has been working on with lead customers. How do we manage complex hashed memory systems where there might be 8, 16 or more DDR controllers in a way that you can run in simulation? And we've created hash defeating content so that you can run with like one DDR controller and still create stress tests, even though in your real system it's going to be a hashed memory architecture. You may want to test the operation and of the system cache in an interconnect, as well as its relation to the caches in a cluster. You may want to explore, if you're using MPAM, you may have different MPAM configurations, and you want to check that the throttling mechanisms in MPAM work as you hit the bandwidth or caching limits that are set. There's a big software overhead, as I said, with PCIe. CXL is based on PCIe, so you need a lot of support to be able to create tests for these out of the box. Once you've created your stress scenarios, you need to understand the results. So whether that's graphical analysis just to check the scenarios you've created, because it's very easy to create scenarios, and a lot of you will be familiar with the problem that you can create what you think is a constrained random UVM test, and then when you actually look at what it's doing, it's not quite doing what you thought it was going to be doing. We need to have the same kind of sanity check in performance tests, because you want some kind of randomization in your performance tests to get all of the permutations explored. Well, you will need to be able to do sanity checks to make sure the bandwidth you're requesting is as you expected from the test. You need batch performance checking, so that once you've got a regression for your performance testing, you can actually run batch checking in the same way that you have verification checks. And if somebody checks in a new piece of code and it breaks the performance regression, you've then got to go and debug it in exactly the same way as somebody introduces a new piece of RTL into a verification regression. You have checkers that will fire and find bugs, you go and debug it. And so you need the graphical analysis for that as well. So you need graphical analysis to debug and root cause the performance issues. And that basically is where System VIP from Cadence, that's what I've been working on for the last 10 years, to build a suite of tools with some help from our R&D, obviously, to address these kind of problems. So with that, Mike, I'm very happy to take questions if there are any in the chat. I don't know.
We've got a couple of questions, Nick, but unfortunately we're out of time because it's 12:30 now. Okay. So what we'll do is we'll send those two separately. The two questions that was sent to you, and I'll just read them out so people know, and we may be able to post them later. Is for cache coherency, which is the best practice and tool, and the second one, chiplet. Is it correct to say a lot has to be standardized as far as verification is concerned? Functional model, deliverables, format, interoperability, etc. So we'll send to you that. We'll send you those separately, Nick. You should send. Yeah, they are good questions. And then what we can do is when we tell people the slides are available, we can include your answer in that. If that's okay.
Yeah, sure, no problem. Happy to.
Yeah, we just want to keep the time because I think the day is
Yeah,
online. So hand over.
absolutely.
No,
Okay.
thank you very much. Thanks, Nick. Thank you. Bye. Hi. So, should you ask Dave to share his screen?
David, I believe you're the presenter. You may go.